Our next speaker, Jacob Marks, is a machine learning engineer and developer evangelist at Voxel 51. At Voxel 51, Jacob created Voxel GPT, an LLM-powered AI assistant for computer vision. In addition, he leads open source efforts in vector search, semantic search, and generative AI. He's a top writer in AI or Medium with 6,600 followers and a LinkedIn top voice in AI. Prior to joining Voxel 51, Jacob worked at Google X, Samsung Research, and Wolfram Research. In a past life, he was a theoretical physicist. In 2022, he completed his PhD at Stanford, where he investigated quantum phases of matter. All right, so let's hand it off to Jacob.
Hey, everyone. I'm Jacob. Thank you for having me, and thank you to Christy and the Zilliz team. Really appreciate this opportunity. Also, Mihail, awesome talk. I resonate with your passion for building production-grade, multimodal, enjoyable-to-use systems. And on a more practical note, I have definitely encountered that text issues problem a ton of times. Even making this particular image, I had to remove some really, really bad text from DALL-E 3. So I'm definitely going to be using Storia Labs. So today I'm going to be talking about using vector search to understand your data better. And the title says computer vision data, but I'm really going to go a little bit broader than that. I'm going to go pretty fast because there's a lot to cover. But the main gist of the talk is RAG is not the only thing that vector search is useful for. My name is Jacob. Christy already gave a full introduction, so I won't dwell on this, but I'm a machine learning engineer and developer evangelist at Voxel 51. And at Voxel 51, we are the lead maintainers for the open source toolkit FiftyOne. It is a data-centric AI toolkit for building computer vision visual data sets that are very high quality. We're a small team built out of the University of Michigan. We have expertise both from the industry and academic side. And our mission is to bring transparency and clarity to the world's data. So we want to ensure data quality and to enable data-centric workflows. To that end, we have built FiftyOne, which is an open source toolkit for curating, visualizing, cleaning, finding hidden structure, and evaluating models on your data. So it helps you to take your data and understand it better, find the best subsets of that, find issues and get rid of them, and to train better models using that data. So my first experience and our first experience as a company with vector search was actually in vectorizing our documentation. So this is something that a lot of people are doing these days. We did this back in April before it was popular, not as early on as Mihail and that whole crew got into AI, but we were pretty early on in this, and this was, we were like blown away by what it could do. We also used vector search when we made Voxel GPT, which Christy mentioned, as a way to using LLMs to query your computer vision data sets. So instead of having to know the syntax in order to get the specific subset of interest, you could just ask the model and it would turn your text into this specific query for you. So like a text-to-SQL generator, but more complicated because computer vision data is unstructured. And this is the outline. So I'm going to talk about data, and more data. And then we're going to talk about how you go from RAG to richer understanding, and then some applications of vector search for exploration. I'm going to go pretty fast because there's a lot to cover. At the end, I'll show you a brief hands-on demo, but I'm going to show you some GIFs from the FiftyOne app before that. We're currently in the middle of AI's Cambrian explosion. No matter how you slice it, whether you're talking about the number of papers per month, the size of the top models, how often the benchmarks are changing, how often the top models and the state of the art is changing, things are changing rapidly. And the state of the art seems like getting set every single day. So you can see in just for 3 of these benchmarks that we have here, in every single one of them, the rate is increasing at which the state of the art is being set. And one thing that people don't think about a lot, but a huge part of the equation is data quality. So oftentimes, the thing that puts a model over the edge, because the differences between the top performing models and the second and third are so small these days that the big difference maker can be if you're cleaning and curating a high quality data set to train on. And these can be things as simple as labeling issues. They can be a mistake in how you're basically classifying your images or your text or whatever else, or it can be duplicates, or it can be low quality samples or something else entirely, outliers, you name it. In other words, bad data is the villain of machine learning. And data is really where models get their power from. It's what you train them with. It's where you evaluate them. And yes, this is another example of where I used the one of those weird text blurring and removal things. And Mihail's, like the story AI would have been a huge benefit for me in making this image as well. Data is king. So FiftyOne puts data center stage. It makes it easy for you to filter, clean, exclude, curate, select, and really understand your data. So here is a GIF from the app. And this is showing how easy it is to filter your data in the app. You can filter by any properties you'd like, be they quantitative, be they classifications, whatever. And all of this is also possible via the Python SDK. So everything that is possible via the app is also, it's basically just a UI wrapper around the Python library that allows you to do this querying. You can visualize your data. You can look at hidden structure. So here we're going to look at some embeddings that we have dimension reduced using UMap. And you can lasso select a certain set of them, certain like localized area. And you can see that that particular cluster corresponded to food that was on plates. And you can do fine-grained model evaluation. So you can go beyond the one number metrics and you can get down to individual sample level and detection level information. You can see what's going on individual predictions. Okay. We're gonna switch gears a little bit and talk about RAG. So if you're here, you probably know what retrieval augmented generation is. So this is the reason that vector search became one of the hottest things in the world. It is essentially a way to improve and increase the memory for large language models. And it works by basically you have the language model, you have a prompt from the user, that prompt gets embedded. Maybe there's some pre-processing, some post-processing, but that embedding is compared to your set of vector embeddings that you have separately, and the relevant information from the results of that vector search are fed in to the model as context. So this is a way to extend from short-term memory to long-term memory. But a key thing about retrieval augmented generation is that it's non-interactive. So the user does not interact directly with the vector store. They interact with it by proxy. Basically, they ask questions, and whatever happens behind the scenes with the vector search, they see the results from the large language model. RAG works for two reasons. One is embeddings. So embeddings are a way to capture some representation of your data. Depending on which model you use, it represents different facets. It can, if you're dealing with images, it can represent either pixels and patches, what's going on in the individual RGB values and the small clusterings, or it can be more semantic. For text models, there's text models for all different types of languages. There are some that are specialized to code, and each of these models represents different features of the data. But basically, you have text in or data in, embedding model, and then vector out. The second reason that it works is vector similarity. So vector similarity, the fact that you can compare multiple vectors for the original data inputs, and that the similar vectors tells you something, or it has some bearing on the closeness in some sense for the individual original inputs. So if you take two text inputs and you embed them and you look at the closeness, whether you're looking at the cosine similarity or the Euclidean distance or the dot product, whatever the other metric is that you're interested in, then you find the most similar vectors. They're most likely going to be close to each other in a semantic space or in some other type of space. And it turns out that these two properties, the embeddings and the vector similarity, can actually be useful for so much more. So for images, embeddings are also incredibly useful. And this is an example here where we are looking at a latent representation of a model for MNIST. They're like these very low resolution images of digits here, and you can do an encoder decoder setup and you can get out an image at the other end. But basically the embedding is giving you some representation of your image data. You can also do multimodal embeddings. So you can look at embeddings for text and images put together. And clip contrastive language image pre-training from OpenAI is a way to do that with images and text. But you can also do that with other modalities. So ImageBind from Meta recently came out, which has 5 different modalities. And you can basically look at images, videos, audio, all these different things in the same type of space. You can compare them, you can do cross-modal retrieval, all of that. Now, vector search comes into play for data understanding, and I'm saying computer vision here, but really I mean visual data. And by that I mean any way that you want to interact with and explore your data in a more interactive sense. So instead of having the vector search be on like this non-interactive, behind the scenes by proxy thing, expose it and get to see your data by virtue of that vector store. So FiftyOne did just this. We integrated with Milvus, as well as a couple of other vector databases, but today I'm going to be showing you a lot of stuff having to do with Milvus, and we love Zilliz. We use them all the time. I'm going to show you a bunch of GIFs that use Zilliz, and it's great. But we integrated that into our capabilities so that users can do this within the FiftyOne app, through the SDK, whatever. So open source product, you guys can use this all for free. This is all free. You can try it out, pip install FiftyOne. So here are some examples. So this is just a few examples that I thought of, but I'm sure that you can think of your own examples, and the sky is really the limit with all of this. So the simplest thing that you can do is image similarity search. So you take an image from your data set and you find similar images throughout the data set to that image. So here we're selecting a dog, and then we're doing a similarity search, and behind the scenes, it's using a Milvus vector collection, and it is querying that with this index, this particular vector from the index, and it is finding the results, and it is returning to us all the images that were in the K most similar. And you can configure what metric you use, you can configure the K value, you can configure all that stuff. You can also use images that are not from the data set. So you can take an external image, either from a URL or from another thing that's on your computer, and you can compare that. Same idea here. What you're doing is you're embedding the query, and you're comparing this to your pre-computed set of embeddings. You can do object similarity search, so you can look at the object detection patches, whether they're ground truths or predictions from some model, and you can find things that are similar to those. So one example here of how this might be useful is if you're doing like facial recognition, or you're trying to find a person throughout a bunch of data sets, they're not going to take up the entire image. So if you compute embeddings for the entire image, it might not always be similar to embeddings of that person on their own. You can do things like robust OCR document search or semantic document search. So you can embed the little text blocks, and this is very similar to how we embedded our documentation. This is more like a typical use case, but it just shows you that you can make it visual. You can interact with, and you can get results that you can then see where on the page, so where in each of the pages in your large document or set of documents these results come from. You can do semantic search, so you can use text and query and get images that are close to that. So here we're going to query for animals, and then in this case we have used a clip model so that this is multimodal, and then we are embedding the text, and we're comparing that embedding for the text to all of the embeddings for the images. You can do cross-modal retrieval. So I'm not sure that this is actually going to work here because it's video. Let's see. So here I am using ImageBind, which I mentioned earlier, and we are selecting an audio clip of a train. And then we are embedding that, and we're comparing that embedding to all the images in our data set. We're getting out all the train images. You can even do things like probing perceptual similarities. So if you have different models, those models represent data differently. You can look at how those models perceive the world, essentially. So some models, like CLIP, are very semantic. So they're going to capture high-level details, but they won't actually capture what's going on in a pixel level. They won't capture the palette of the image, things like that. You have other models like ResNet, which are more traditional computer vision, like convolutional neural networks, very pixels and patches, and those will get the palette right. They'll get the coarse details, but they won't get any of the meaning right. So they'll give you things that have very off in terms of their like what the actual content is. Maybe you'll have things that they're all plates, but the actual food on it, one is a bunch of noodles and the other one is steak. And that's maybe not what we want. Maybe it is what we want, depending on the application. Here's another model, just showing you what the results look like when we change up the model. You can compare model representations. So here what we're doing is we have two models. One model which we are doing the vector search with respect to the embeddings from. And the other model, we have taken the embeddings and dimension reduced everything. And we are looking at where within this set of points in this lower dimensional space, the vector search results from the first model are. So you can see kind of where they are relative to each other. You can kind of see where in the space of how the first one is representing data or the second one is representing data, the other one has similar results. And so in this case, we can see that they're not all clustered together. So there is a difference between how the models are seeing the world. You can do things like concept interpolation. So now we get into more experimental things where you can take two text concepts and kind of interpolate between them using the embeddings as a starting point. So you can say, hey, I want to start out with, let's say, a husky and a chihuahua, and I'm going to linearly, or however else I want, take some value in between those two embeddings. And by proxy, I'm going to take some concept in between those two original concepts, and I'm going to query my data set for that. And you can do things like traversing the space of concepts. So you can start with an image, and you can add text concepts to it iteratively in whatever weights you want, and then you can query the data set for that. So you are using, again, this is a vector database on the back end. You are combining your embeddings for text and images and whatever modalities you want in whatever ways you define. Some of these things can be well-defined mathematically, some of them cannot be, and this is an area of active research. But this allows you to understand your data better, to understand the models better that you're dealing with, and just in general to more dynamically explore the space of possibilities. So before I do next steps, I just wanted to show you guys one hands-on thing. So here, for this talk, I took a bunch of base64 encodings for emojis and super res them 10x, computed the embeddings for them. So we can do this. We can, do our semantic searches on these embeddings, and we can find all of the embeddings that are similar to whatever our search is. You can specify your thresholds if you want to. You could even do the same concept interpolation thing that I was just looking at. So we can do, for instance, reverse image search. Let me get rid of this and do reverse image search. And I can take this one, and I'll put this in here. You can see those are the images that it thought were similar based on that particular model and that particular embedding that I was using. We could even do things like the concept interpolation. So for this, for concept traversal. So I'll set the initial image to this one, and then we'll add a little sad. You can keep on going with this. This is just to show you that this is real. You can play with it dynamically in real time. All right. Okay. So I wanted to thank Zilliz again, Milvis, the Unstructured Data Meetup. Really appreciate being here. This has been an incredible opportunity. Do I have one more minute?
You have, well, your time is up, but.
1 minute? Okay. Upcoming events tomorrow, if you're free, we have 2 virtual events, one on authoring data-centric applications like the concept interpolation and concept traversal ones that I just showed you. If you want to learn how to make those, go to that. And then there's one on transforming computer vision with LLMs with Data Science Dojo. Join the community. Start us on GitHub. It's an open source project like Milvis. Follow us, try FiftyOne, it's free. We also have shirts back there. So if you want a shirt, go by Michelle. She is very nice. She's great to talk to. We've got lots of shirts, but not enough for everyone. So first come, first serve. And thank you so much.
lot of questions here. Quick question to kick it off. So Mihail talked about generative AI, and you talked about image search. Could these tools be used for synthetic data generation?
Yes, they could. So once you use these embeddings and you're able to find similar samples, you can look at the embeddings in the latent space, and you can kind of find some spots in the latent space that are not as covered. So basically patches of the latent space that have worse performance on certain models. And you can use those latent representations combined with the GAN or some other generative model to generate new images or new samples to fill those spaces, essentially.
Fascinating stuff. Questions?
We thought of combining multiple small models to essentially a mosaic latent space. So like creating, instead of like having one large model, having a full global representation of the space, having smaller models that, let's say, focus on subsections of that latent space.
So I'm not, if I understand the question correctly, you're asking about combining model representations in different latent spaces, and that's definitely something people do. So one of the models I showed you was called DreamSim. It's a spotlight paper at NeurIPS, which is coming up in a month, and they combined the latent representations essentially of three models. It was Clip, Dino, and OpenClip, and then they fine-tuned with LoRa on top of that. But the basic idea was combining the three representations of those models and getting better representational power by doing that.
Can you just briefly say what the name of that paper was again?
Sorry, what is
the NeurIPS paper that you just said?
Oh, so the paper is called DreamSim, and the data set is called Nights.
Thank you for the presentation. So I have a quick question regarding the models. For the samples you showed, are they based on the model that you guys trained in-house, or are they just open source, pre-trained models?
These are all open source pre-trained models, but if you have special purpose data, so if you're doing your own application, manufacturing or something else, then you will likely get much better results if you fine tune your own model or train from scratch and then use the embeddings from that model.
So, do you guys have plans to use your own embedding models to provide some performance that are better than existing tools?
I won't say no, but we really just want to do whatever it takes to help people to build better data sets.
Thank you.
For that concept traversal, you could really just put in any word?
Mm-hmm.
Wow.
How do you guys compare to like a coactive?
To what?
To coactive? Like, have you heard of coactive?
I've not.
Okay. Never mind.
I'll check them out.
Get the question. I didn't ask
it. Can you help convert an image to just give us an array of text that you can extract from the image?
So you want to go from image to text? Ooh, that's a little bit different of a problem. We should talk about that offline, but that is a very interesting thing to work on.
Yeah, because again, like for our use case, users are looking for a good prompt to generate an image based on an example that they like. Mm-hmm. So
yeah, there's like a clip explainer is one thing that people do.
Good prompts are hard to come by. Any more questions? Okay.
Clip interrogator.
Quick question. So data sets that can clean through, I saw images and it looked like you were doing cleaning through text data sets also. Can you do different language?
We are primarily visual data. So if anything that you can visualize with text, but mostly images, videos, point clouds, so LiDAR, radar.
So could you just explain the concept traversal use case again?
Yeah. You take the embedding vectors for the image and the different text concepts, and you combine them mathematically, and you have some destination vector that you then query your vector index with respect to. And there are sophisticated ways to actually do that combination. There are like there's the naive way, which is just like adding them together, but there are much more sophisticated ways of doing it that are much more like mathematically grounded.
The demos were great. Can you talk a little bit about some real life applications, what people are actually using it for, or what domains they're using it in? Just
all sorts of domains. People need high quality data everywhere. So everything from manufacturing to agriculture to healthcare. We have people and companies from individual hobbyists to Fortune 100 companies.
And in terms of the sizes of the data sets, is there any practical limit in terms of what you can do locally?
No, it's a logical data set structure. So the FiftyOne data set points to the media on disk. You can also, with FiftyOne teams, work with things that are at like in Google Cloud buckets or S3 buckets or whatever else. So people have up to 1 billion samples.
Thank you.
I can ask a question. Hey, great talk. How do you evaluate the retrievals for the images that you're querying?
Great question. So there are specific like benchmarks that cover and try to quantify the quality of your retrieval in these multimodal settings. I would look at those. I think that Hugging Face has a good listing of them.
We have time for one more question. Query?
It's probably a simple question, right? Because you just show you have several features and you just want to do some interpolation, right? Usually when we do, say, GAN, right, we have some correlation between different features, but it seems like your product is already, say, to the next level. So how do you regulate or regularize the correlation between different features when the user try to tune the style? Yeah.
I'm not sure I understand.
Like when you generate the image, right, you can say add more sadness, right, or some other emotion to your image, right? So we have different features, and usually we have some correlation when we try to do the interpolation. When you add more sadness, probably the other feature also got changed. So what do you tackle?
It didn't change. No, so the embedding for the initial image was preserved. That was untouched.
Okay. So you didn't see any like sad effect, like the correlated effect. You didn't see it at all.
I'm not sure what you mean by correlated. We can talk about this offline.
Yeah, sure.
Yeah.